The world as you know could not, would not exist without something we depend on every day, every hour, every moment of our life, and that is called electromagnetic energy. Every time you use your phone, watch TV, send a text, you're using this energy, and its existence has helped shape the world you know. Traveling in waves, they span across a large, broad spectrum, from visible light to X-rays and gamma rays. The sun is a source of this energy, and it encompasses the full spectrum, its electromagnetic radiation bearing down on Earth constantly. However, our atmosphere protects us from the higher energy waves that can be harmful, that are called ionizing, meaning it can even knock out electrons from atoms. Our atmosphere's gases absorbs or reflects most of the radiation energy, the most important gases being water vapor, carbon dioxide, and ozone. Only atmospheric windows can pass through our atmosphere, like visible light, that have the right wavelengths in the spectrum to pass through. Regions of energy in the spectrum that we can't see, called spectral bands, are represented by false colors that can be analyzed by scientists to help better understand. Digital cameras have sensors that picks up the brightness of colors and records them as numbers. They later combine these data to form images we can see. Instruments on some satellites can also pick up natural color, visible light that we would see if we were in such a position. Sensors can pick up brightness and record them as numbers, so if there is a light that isn't visible, the sensors will combine the data together into images we can see. Composite images are formed from different instruments. Spitzer, Hubble, and Chandra space telescopes are examples of such. Spitzer offers infrared vision, Hubble is natural light, and Chandra is X-ray vision. Combined, these make composite images that help scientists better understand. Sometimes data is best represented as a scale of values, so scientists can best visualize the data. The colors are not always very exact, but they are arbitrary, so they can help better the scientists help understand the data. Energy, the measure of the ability to do work, travels in waves. Two important ones being mechanical waves and electromagnetic waves. Energy comes in many forms, changing from one to another. The type we call electromagnetic radiation are transported by electromagnetic fields created by charged particles like protons or electrons. Mechanical waves are caused by disturbances in matter, being solids, gases, liquids, or plasma. The molecules bump into each other to form the wave that travels through the matter called a medium. Electricity and magnetism can both be static. A changing magnetic field can create a changing electric field, and vice versa. These two are linked, and together they form electromagnetic waves, which don't require a medium to travel through. Scottish scientist James Maxwell developed Maxwell's equations, the theory between the relationship between the electric and magnetic fields. Heinrich Hertz performed experiments putting Maxwell's theory to the test. Applying them to radio waves, he discovered radio waves are the same speed as light. Light is made of photons, pockets of energy with momentum and no mass. Polarization is a measurement of the electromagnetic field's alignment. There are three ways of describing electromagnetic energy: frequency, wavelength, and energy, which are all mathematically related. Frequency is the number of crests that pass a point in 1 second, measured in hertz. Wavelength is the distance between crests and waves. And electron volts measure energy in waves, the amount of kinetic energy needed to move an electron through 1 volt potential. Every time you use a microwave to cook food, you're using microwaves, causing a forced rotation in the food to make it cook. Microwaves are a type of electromagnetic waves. They're a band in the higher energy spectrum of electromagnetic waves, and under microwaves there are also subbands. These are used in your GPS, microwaves, and science-related instruments. These can penetrate through dust, ice, clouds, grit, haze, snow, and rain, allowing the scientists to observe without distractions. Radars also use these waves, sending a pulse outward and then receiving any of the waves that bounce back. These are called active remotes. Passive remotes are simply observers that absorb the electromagnetic radiation. These waves also help scientists develop the Big Bang Theory after hearing a background noise that was coming from all around but not changing in intensity. This was the cosmic microwave background radiation. Every time you tune into your favorite radio stations, you're listening to a very special sort of electromagnetic waves. Radio waves. Radio waves have the largest wavelengths among electromagnetic waves, ranging from a football to even larger than our planet. Heinrich Hertz proved these radio waves were a type of electromagnetic wave in the 1880s. Planets, asteroids, and stars also have changing magnetic waves, meaning they can also produce radio waves. Telescopes also look at planets, asteroids, comets, and stars using radio waves, which allow scientists to determine the composition, structure, and motion. They're bigger than optical telescopes because the radio wavelength is larger. In order to make a higher resolution image for scientists, they combine smaller telescopes to make an array, which will act as a single large telescope. Radio telescopes differ largely from optical telescopes, detecting something called quasars as well, which has large amounts of energy. While using your remote control to switch the channels while you watch TV, you're also using infrared waves, another type of electromagnetic waves. They are a type of light, just